I'm pleased to present as a video the conference I was expected to give for the conference. First of all, I would like to thank Professor Achu, who has done a lot of work for this organization of the symposium, including the one we are giving in terms of video. So great work and congratulations to make it as a conference by video. First, my presentation is linked to this novel carbon nanomaterial, and as you can see for the guidelines in terms of conference is given on this slide with the different type of carbon-based nanomaterials that will be followed by the synthesis, purification, and characterization. And the first application is linked to the printing of carbon dust as ink. The second application is related to the enhancements of thermoelectric and also dielectric effects with carbon dust. And finally, the last application is linked to the hybrid rocket fuel with carbon dust as an additive. And this would be conclude at the end of my talk about these different applications and the future work. And the last slide will be linked to the acknowledgement based on the agency that was able to support our research. So saying that the carbon-based nanomaterials is linked to the different type of carbon dust has been performed since 1963 up to the most recent one is 2004. And 2004 means that from now on the number of papers published, as you may expect, is huge. For 2019, we can count more than 1,000 papers published on different aspects of the carbon nanomaterials. So what is the history for the preparation of this carbon dust? This is linked to Sue groups in Clemson University. He was doing the purification of nanotube. What he found out by TLC was two spots, and that was related to the carbon dust. And one way to look about the photoluminescence property was to shine light onto the carbon dust using a filter, and this is the first part here, that using filter he can detect different wavelength of the carbon dust. Another way to do the same type of experiments is to use a specific wavelength for the radiation, 400, 450, 500, and as you can see, there is a good correlation between the A and B part of what I have shown. So this important was in 2006, in fact, has been published. And if we ask the question, what are the properties of the carbon dust? And this is shown on the next slide. So small nanoparticles, 1 to 10 nanometer. This is luminescence property are excellent. High biocompatibility, high tunable surface functionality, so have many type of functionality on the surface. To prepare it, this is easy and versatile. And finally, there is a lot of electron donors and acceptor on the carbon dust. So saying that, if we think about application, as you can see on the left side, biomedicine, sensor, catalyst, optronics has been really, I would say, described in the literature from 2006 up to now. So what we need to look now, this is really on the next slide, will be related to the synthesis and purification of the carbon dust. And as an example, there are two approaches to have a look at it. And the first approach is related to the top-down approach, and the second one is linked to the bottom-up approach. As you can see, for the top-down approach is we start with a large molecule and using laser ablation or electrochemical technique or arc discharge, we can reduce these large molecules to the small particle, and we have the carbon dots formed between 1 and 10 nanometer. The second approach is the bottom-up approach. That means we start with small molecule, and we will see in the next slide the way to produce it, these carbon dots. Small molecule, and the main procedure uses ultrasonic, hydrothermal, and microwave pyrolysis. But I must say that if we look at the number of papers published using the hydrothermal approach is quite important. Maybe 85% of the paper that is published for the bottom-up approach. Now the next slide I will present the 4 different ways to prepare the carbon dots, and in my group we have using these ways, including also sonication, not only thermal effect and microwave, but also sonication. And we are able to prepare at the moment about 40 different types of carbon dots in terms of preparation. The one I want to mention first is a carbon black. So this is formed using carbon powder. We use oxidant, sulfuric acid, nitric acid, and we use the dialysis for purification, and we form the carbon dots. And the next slide will give you the characterization of this type of carbon dots. A second type is the gel-like carbon dots using, again, the first one was related to top-down, the second one is linked to bottom-up approach. So using citric acid and ethylenediamine, and heating the mixture at 100 degrees centigrade for 50 minutes, we use argon to make sure that there is no oxidation of the compounds. So in that way we prepare the gel-like carbon dots. Another way with the yellow carbon dots, so again citric acid as the precursor, and we add the 1,2-phenylenediamine. Again the ratio 1:25. I must say the previous one was ratio 1:14. So 1:25, and again using in this particular case sonication to produce carbon dots. And the next one is carbon nitride dots, and we can use urea and also citric acid. And microwave or pyrolysis means hydrothermal heating the mixture so we can produce carbon nitride. So we'll discuss mainly the black carbon dot, which is top-down approach, and also the what I call bottom-up approach with gel-like, and the yellow carbon dots. And this is presented on the next slide. And there are 4 different ways to characterize it. Absorption, UV-vis absorption is one way, fluorescence is another way, and finally FTR is the third way. So I just mentioned about the 3 of the preparation: black, gel-like, and the orange carbon dots. So if we look about UV-vis absorption for each of them, we have 2 main peaks. One which is the C-double-bond-O, which is related to assigned to N-pipe absorption, and we have also the CC. This is pi-pi interaction in the low wavelength region for each of these carbon dots. For fluorescence measurements, so you can see that depending on the wavelength of the excitation, there is a shift of the photoluminescent spectra. And this shift is quite important for top-down approach or bottom-up approach. So we have the bottom-up here, and we see this shift from when we excite a different wavelength, from low wavelength to high wavelength of excitation. There is a shift for the luminescence. As you know, pure fluorescence molecule, there is no shift. Excitation, different wavelength. The photoluminescent is always at the same wavelength, but not for the carbon dots. And the hypothesis we attribute it to a surface state, I would say surface state formation, and the second is linked to the possibility of producing fragments that is fluorescent. The last one is Fourier transform infrared spectroscopy using attenuated total reflection to do this, to get this spectrum for each carbon black. And this is linked, there is a correlation between FTIR spectra and XPS. So just to mention that, for example, the OA crew for the black carbon dust, which is again top-down approach, and we look the formation or possible formation, yes, C double bond O, C double bond C, and if you look for the gel-like carbon dust, there is a huge peak related to nitrogen or NH bonding. And if you look the difference between FTIR and the gel-like of the black compared to gel-like, the gel-like shows a huge peak for the nitrogen doping. And for the orange carbon dust, that is not so important. And there is a correlation between these measurements and X-ray photoelectrons measurements. The reason I'm saying that is because with black we have the carbon 1s, the oxygen 1s, but the nitrogen 1s is a very, very low, so we were not able to detect it. So there is a correlation showing that Leblanc carbon dust doesn't see by FTIR a huge peak due to nitrogen doping, but the gel-like, yes, we see it. So this is the AFM and TEM measurements, because if we want to know the size of the particles, we need to use these two methodology, atomic force microscopy and transmission electron microscopy. Why? Because AFM, the resolution is great for the z-axis, and the TEM, there is a high resolution x-y axis. As you can see for the AFM and TEM, the black, gel-like, orange, there is quite a good correlation between these two microscopic techniques. Quantum yield, very high for gel-like, but low for the black and the orange carbon dust. And what is showing for this black and also gel and orange, this is the zeta potential, and zeta potential is around minus 12 millivolt, so which shows that we can have a good sparsity of these nanoparticles in water or hydrophilic solvent. So the guidelines now follow is related to the printing with carbon dust as ink. So the point is, if we change the ink from a printer as an example, and we look if there is a possibility to print the text directly with gel-like carbon dust, the answer is yes. Now, first of all, you see the paper that we use for the print, and with UV light, or I would say white light, we don't see anything. Now, if we print out on this paper the text, as you can see that this printout is very well executed, it's very well, the precision is great. Why? Because again, if we use white light with this text here, we don't see anything. This is the same as what I said at the beginning. If I use UV light, that's the text, it's printed out. And what is important is the fact that if we take one drop of water and we can erase the text, and we can use the same paper to reprint it, and with the same good, I would say, presentation of the text. So the other point is to do the 3D printings. So we use carbon dust again that we mix to polymers, and using the 3D printing system, we're able to make the Statue of Liberty. When we shine light, white light, we don't see any color emission coming from the carbon dust. And when we use the blue light, we can see the experimental one, which is related to the yellow carbon dust. Same thing if we have carbon dust, gel light, and we have some beads, polymer beads. There is adsorption of the carbon dots into the beads, and with white light we don't see any change in the color. If you use a blue light, you see this particular case, we can see the blue emission coming from carbon dots. Another application is related to the fingerprint. So again, having the gel-like, and if we put our fingers onto the gel-like and you put it on a piece of paper, using white light we don't see any fingerprint. With blue light, now we can see fingerprint. So for two of my graduate students, two different fingerprint. We can use it also for nail polish, because if we mix the nail polish with carbon dots using white light, so we don't see any color effect. If we use carbon dots mixed to the nail polish, so again we see the luminescence from the carbon dots. So two, what I call application that is probably straightforward, but it is important to mention we can use this methodology for printing, 2D or 3D printing. And the next part is, during the last 12 months, we changed our orientation to study the application of carbon dust by looking at the enhancements of thermoelectric and dielectric effect, and second, by also looking at the possibility to have a good efficiency of our carbon dust on the hybrid rocket fuel. So first one I would like to talk about is related to thermoelectric effect. We know that if we have a heat source and a cold source, that there is a direct conversion of heat differentials to electric voltage. And this is what we call the thermoelectric effect. And we can have a system with different modules to gather this electrical conductivity and to measure it. So the main point is related to first to do the measurements of the conductivity, electrical conductivity, and the Seebeck coefficient characterization. And the second measurement important is the thermal conductivity. Why? Because one case, electrical conductivity, is directly proportional to efficiency or thermoelectric effect, and the thermal conductivity is inversely proportional to the efficiency. So if you're able to increase electrical conductivity and to lower the thermal conductivity, so that means you would have a much higher thermal effect for the system. And using the carbon dust, we have shown that yes, there is a possibility. As an example, we can see the electrical conductivity with a current if we use which is the pure bismuth telluride, compared to 2% carbon powder, which is not carbon dust. This is nanoparticles of 100 nanometer, so there is a small increase. But when you use the carbon dust 3 nanometer, prepared with black, what I call black carbon dust, I have shown before, this increase is quite important. And the way to look at it is the power factor. And if you compare the carbon dust added to compared to the pure bismuth, and we're talking about 2% incorporation in the matrix. So we have an increase of 16%. Why it is important? Because we have many applications. For example, the drink coolers, the recharging devices, space probes, power, solar power, medical application, and our space application. The other parameter, physical parameter that we have done some work for the last 6 months. The second property that physical property we have measured is the dielectric effect of carbon dust. So carbon dust has been prepared by this methodology from Shukla and related to citric acid plus the primary amine as a precursor, and that means that after heating at 250 degrees centigrade, 1.5 hours, we have left with our carbon dust. And purification has been performed using dialysis bag. One parameter that we have measured was related to the switching time, and in all cases that we have performed with 0.1% or 0.05%, as you can see, we have an increase of the switching time. For the AC conductivity, low regime in terms of frequency, no difference in this AC, but with high frequency, there is quite a large difference between the introducing carbon dust in the matrix into the ferroelectric liquid crystal compared to 0.05% compared to the non-doped, much higher frequency. The second point I want to mention is related to the value of this dielectric permittivity versus the frequency. And again, we have an increase of 11.5 and 20% enhancement when we increase the concentration of carbon dust. For the absorption spectrum, again, we see this increase when we use 0.1% of about 23% increase of this value of epsilon second. And third, if we think about the spontaneous polymerization versus the temperature, again, an increase of 10.5 and 15.5% when we introduce the carbon dust. If we look the Goldstein mode relaxation frequency, and we can see that there is a reduction on this value. And for the term of dielectric strength, this dielectric strength increase, as you can see, for 0.1%, much higher than compared to the non-doped ferromagnetic liquid crystal. And this increase is will go up to 65 degrees centigrade. And finally, the variation of the gamma for the in function of the temperature. Again, there is an increase of 79% increase when we add the 0.1% carbon dust in the matrix. So there is a huge effect of introducing the carbon dust into the dielectric system. So different matrix might be the way to see different dielectric effect, and this one is only related to one matrix, so it can be might be interesting to work with different matrix. So the overall parameters that we just measured is linked to the fact that carbon dust probably induce what I call a dipole, induce the ferroelectric liquid crystal dipoles there, because the carbon dust is a system that conducts the electricity. So the other point is related to the hybrid rocket fuel. So when we think about the rocket fuel, means that first of all, rocket is linked to aircraft. It's related to the space also, aircraft. And we have always the question is, what is the meaning of hybrid rocket? Well, this is linked to the propellants. We can have a solid propellants, we can have a liquid propellants, or we can have a hybrid propellants. In our case, we are talking about the hybrid propellants. Saying that, the way it works is the following. So we have a liquid oxidizer, and we have a chamber related to what I call the port. And there is a possibility to inject the liquid into the port for combustion measurements. So first of all, the idea is to have, for example, for the liquid oxidizer, we can use nitrous oxide at room temperature, but at high temperature it's better to use at low temperature, it's better to use the liquid oxygen. And we introduce with this control valve the liquid oxidizer into the chamber where we'll proceed the combustion. Combustion starts with an ignitor, and as you are aware, Combustion means a lot of energy release. This is an exothermic process, and that means that at the nozzle we will have a high concentration, or high pressure, not concentration, but high pressure of the following the combustion, high temperature also. And that means we'll have possibility to look about the generation of the hot gas at the exit. So that's the main principle for this hybrid rocket. We use a liquid rocket engines, and we use, in fact, in our experiments, the oxygen for the oxidation. And as you can see, this is simpler in terms of mechanics, reduce the fire hazard when we use the liquid one, only a single liquid, higher fuel density, easy inclusion of high energy additive, solid fuel present, reduce contamination hazard, and finally, reduce development. So I go right away to the result that we got is related to the average regression rate. And if we use only the wax, for example, compared to without any carbon dust, and having wax to do the oxidation for the combustion, and adding the carbon dust at 2%, we can see an increase with function of different mass of the percentage of the mass of the carbon dust. So that means there is a better efficiency for carbon dust into the system. So that means we have shown that the carbon dust are another class of carbon dust, carbon-based materials. Various carbon dust has been prepared in our groups, depending on the type of application we want to do. Due to excellent photoluminescence, we can see that carbon dust exhibit potential for photoluminescence in 2D and 3D and fingerprint. We have shown that for thermoelectricity and also dielectric parameters, we have an increase of both of these physical parameters, adding carbon dust in the system. And we know that for the hybrid rocket fuels, there will be, this is quite promising for the future, using carbon dust to increase the efficiency of the fuel for the combustion. And the future work, we are interested, of course, to work on these two physical properties that I just mentioned, thermoelectricity and the hybrid rocket in the future. So saying that, I would like to mention that we were happy to have received the NIH and also NSF, and followed by King Abdulaziz University grant. And that means that this is the end of my talk, and I would like to thank you very much for your attention. And God bless you. Be safe. Thanks.